Good morning, everyone. I am recording this meeting. And so this week in your lectures, you worked on Lewis structures. And so today's lab, and I use air quotes when I say lab, because this is more of what we call a paper lab. There won't be any experimental processes via video today. This is just going to be a Lewis structure activity session. And you will view some pictures of some models of molecules. And based on those models, you'll be answering some questions based on those pictures of those models, as well as the Lewis structures for those same molecules that you will have drawn. And so there are some pictures located under the course content tab for week 7 in our eLearn homepage for the lab. And you'll want to view those pictures of those models as you're going through each of the models that we're going to work on today. And so in lecture, we learned that Lewis structures are representations of molecular compounds that shows us how these non-metal atoms that make up molecular compounds, how they share electrons. And so the atoms that make up the non-metal atoms, to be specific, that share atoms, when they share electrons, this sharing of electrons forms what are called covalent bonds. And so covalent bonds, sometimes also referred to as molecular bonds, because these are the bonds that are found in molecular compounds. And so therefore molecular compounds or molecular molecules are often also called covalent molecules. And so when these nonmetal atoms share their electrons to form these covalent bonds, the electrons that get shared are those that reside in the outermost energy level in the atoms. So only those electrons that reside in the outermost energy levels of the atoms will be available for sharing. So why only the outermost electrons? And why not the innermost electrons? So this is the oxygen atom. Oxygen is atomic number 8 on the periodic table, meaning that it has 8 protons inside of the nucleus. Oxygen having 8 protons inside of the nucleus, and as a neutral atom, that means that oxygen also has 8 electrons. And those 8 electrons orbit the nucleus. So I've got the electrons represented here with the letter E with a negative sign, denoting, of course, that electrons are negatively charged, whereas the protons inside the nucleus balance out those negative charges with their positive charges. Oxygen also has 8 neutrons in the nucleus. So the positively charged electrons, because we know opposites attract, are going to be attracted to the negatively charged electrons. But the inner electrons these two inner electrons are going to feel the attraction between itself and the nucleus more strongly than these outer electrons. So these are the outermost electrons in the pink. They're further away from the nucleus. So the outer electrons are further away from those positively charged protons, so they don't feel the attraction as much as the inner electrons. So because these outer electrons don't feel the positive charge of the nucleus as much as the inner electrons do, these inner electrons do what is called effectively shielding the outer electrons from the positive charge pull of the nucleus. So that gives the outer electrons higher energy than the inner electrons. And so they're free to jump and move. And therefore they can be shared with another atom because they're freer. They're not as committed to the nucleus, to the protons in the nucleus, as the inner electrons are. They feel less of an attraction. So that's why only the outermost electrons are available for sharing and therefore forming covalent bonds with other atoms. And so these outer electrons that are available to form covalent bonds by sharing electrons are called valence electrons. Oxygen has 6 valence electrons. So those are the 6 valence electrons. The other 2 electrons, there are 8 total. The other 2 are inner electrons. So oxygen has the ability to share 6 electrons. And so the number of valence electrons is determined by the group number that element resides in the periodic table. So oxygen is in group 6A, and therefore it has 6 valence electrons. Sulfur is also in group 6A. So sulfur also has 6 valence electrons. Hydrogen resides in group 1A and therefore has 1 valence electron. Chlorine, fluorine, iodine, all those elements that are called halogens, they reside in group 7A. So they have 7 valence electrons. Now, the noble gases, they reside in group 8A. And therefore, they have 8 valence electrons. And that makes them very stable in their electronic arrangement with those 8 valence electrons. And so therefore, all other nonmetal atoms that have less than 8 valence electrons aren't as stable as the noble gases in their electronic arrangement. So therefore, they want to achieve that stability by obtaining 8 valence electrons through the sharing process, and therefore through the covalent bond formation process. And so most of these nonmetal atoms are going to want to achieve 8 valence electrons when they make a covalent bond with another atom and therefore share electrons with that other atom, and that other atom sharing electrons with it, and they both complementing each other and making sure that each has 8 valence electrons surrounding it once that covalent bond is formed. And that's what we show when we draw Lewis structures. Now, there are a few atoms that are an exception to this rule that we call the Octet Rule. The Octet Rule is that when nonmetal atoms share electrons and form a covalent bond, the sharing process is going to result in each of the 2 atoms that share electrons with each other having a final total valence electron count around them of 8. Hydrogen is one of those atoms that is an exception to the Octet Rule. Hydrogen, it shares its 1 valence electron with another atom. Hydrogen will have only 2 electrons in its valence shell once that covalent bond is formed. And hydrogen is perfectly happy, perfectly stable, only having 2. Whereas other nonmetal atoms are going to want to achieve the Octet Rule and have 8 valence electrons in its outermost shell when it forms a covalent bond with another atom. There are a couple of other exceptions to the Octet Rule, and one is an alkaline earth metal, beryllium. Beryllium is beryllium is happy with having just 2 valence electrons, just like hydrogen. And beryllium is happy having only 4. Beryllium has 2 valence electrons on its own because it's in group 2. And then through the sharing process and covalent bond formation, beryllium is happy having only 4 total valence electrons. And then another atom, boron, which is a group 3 element, having 3 valence electrons on its own, when it shares electrons with another atom and forms a covalent bond, it's happy having only 6 electrons around it. So those are 3 notable exceptions to the Octet Rule where these elements are happy having fewer than 8 valence electrons. But for the purposes of our class, we'll only be seeing mainly hydrogen with that exception. We won't be seeing a lot of Lewis structures that have beryllium and boron, because basically, not in this chapter, because those elements are metals. Beryllium and boron is considered a metalloid. Beryllium is an alkaline earth metal. So for this chapter, we're focused on strictly molecular compounds, strictly nonmetals forming covalent bonds. And so in our lecture this week, we've practiced drawing some Lewis structures. And so far, I think the Lewis structures that we've drawn have been pretty straightforward and simple, but some molecules can be more complicated. But no matter how more complicated the molecule structure is, we still follow the same basic rules for drawing Lewis structures. And so we'll start off today with a simple molecular compound called methane. Methane's formula is CH4. And so to draw Lewis structures, we're going to follow these 4 basic steps. So first, once we know the formula of the compound that we want to draw the Lewis structure for, we're going to draw the skeleton structure for that molecule. And so we'll first decide which atom in the formula is the central atom. Well, the central atom in the molecule is usually the one that's listed first in the formula. So for CH4, carbon is shown first. So by that general rule, carbon will be the central atom. Now, if you ever have a molecule or compound that you're going to draw the Lewis structure for, if hydrogen is shown first in that formula, then the second atom shown in that formula will be the central atom, because hydrogen, being an exception to the octet rule, and therefore only having a total of 2 valence electrons in its valence shell after it forms a covalent bond with another atom, hydrogen will never be the central atom, because that would mean it will have more than 2 valence electrons in its valence shell once it forms a covalent bond. So hydrogen will never be the central atom, and the central atom is usually the first atom in the formula of the compound. There is a third way or third rule to go by when choosing the central atom. And that is, consider the electronegativity of the atoms that make up the formula of the compound that you're drawing the Lewis structure for. And negativity is a property of elements that means how strongly will that element draw electron density in a bond towards itself. Basically, which element loves electrons more is basically what the measure of electronegativity means. And so there is a periodic table trend for this electronegativity property. So as you move across the periodic table from left to right, electronegativity increases. So that would mean that fluorine would be more electronegative than oxygen because it's further to the right of oxygen. Oxygen would be more electronegative than nitrogen because it's further to the right of nitrogen. And nitrogen would be more electronegative than carbon because nitrogen is further to the right of carbon. Also, as you move from the bottom of the periodic table to the top, electronegativity also increases. So if I'm comparing oxygen and sulfur in group 6A of the periodic table, oxygen is further to the top of the periodic table than sulfur. So more electronegative than sulfur. Fluorine would be more electronegative than chlorine because it's further to the top of the group or column of the periodic table than chlorine. And so therefore, the least electronegative atom in the formula of the compound is usually the central atom. And so those are the ways that you can go about determining which atom in the formula of the compound is the central atom. So for CH4, it's easy to determine hydrogen can never be the central atom, so carbon must be. So to draw the skeleton structure, you put the central atom in the middle, and then use a single straight line to connect the other atoms in the formula of the compound to the central atom. These single straight lines are single bonds. And of course, they're single covalent bonds. Each of these single bonds that I drew, and I drew 4 of them, they represent 2 electrons. So a single bond represents 2 electrons. So we finished step 1. Step 2, we need to count the valence electrons. And so CH4 contains 1 carbon and 4 hydrogens. Carbon is in group 4 of the periodic table, so it has 4 valence electrons. Hydrogen is in group 1 of the periodic table, and there are 4 of them in the formula for methane. So methane has a total of 8 valence electrons. I have already put in those 8 valence electrons: 2, 4, 6, and 8. So I've tabulated my total number of valence electrons needed. I've counted how many I've already put in my structure. And so I am done with methane on step 2. So I've already drew my skeleton, and I put in 8 when I drew my skeleton. And 8 is all that I needed. So I don't have any remaining electrons to put in. So this is our complete Lewis structure for methane. Now, if I was drawing another molecule, Lewis structure, and if I'd drawn the skeleton, I still haven't reached my total required valence electron count, then I would need to proceed on with step 3. And so I'd count how many I've already put into my skeleton, subtract those from the total count, and that'll give me how many more electrons that I still need to put in my Lewis structure. And so then I would want to add these remaining electrons in pairs. And I'll add these as lone pairs around the outside atoms first. So like for methane, carbon is the central atom. These 4 hydrogens are called the outside atoms. In some textbooks, you'll see them also referred to as peripheral atoms. Those are the ones that surround the central atom. So you'll add these remaining electrons that need to be added to your Lewis structure around these outside atoms in pairs of 2, so that these outside atoms not only have the 2 electrons in the single bond that connects them to the central atom, but then they'll also therefore have 3 sets of lone pairs of electrons. Each lone pair is 2 electrons. And if you have 3 sets, that means a total of 6 electrons that you'll put around each peripheral atom, giving them a total of 8 electrons around them. So a total of 8 valence electrons in their valence shell. After you do this, then count up how many electrons you've put in your total Lewis structure. If your octet rule is satisfied for each atom, the central and the peripheral atoms, and that total number of electrons you put in equals your total required number of valence electrons that you've already determined, then you're done with your Lewis structure. Your Lewis structure is correct, and you don't need to move on to step 4. But if you run out of electrons before all of the atoms have an octet, meaning you don't have enough electrons in your structure, then what you need to do is include double bonds in your structure, or even triple bonds if you need to even go a step further than that in order to satisfy the octet. And so what you want to do to form double bonds is take a lone pair of electrons from one of the outside atoms and move the pair into a bond between that outside atom and the central atom, creating a double bond. And count up how many electrons you have. A double bond is basically two single bonds combined. So a double bond gives you a total of 4 electrons. And so do your electron count and see if you have the correct number of electrons in your Lewis structure. If double bonds aren't enough to make octets for all atoms, if there's an atom that still doesn't have 8 electrons around it, then go to a triple bond by again removing 2 electrons from the outside atom and move it into a bond between that outside atom and the central atom, creating a triple bond. And so the best way to get comfortable with drawing Lewis structures is to draw Lewis structures. Practice, practice, practice. And so that's what the whole point of our lab meeting today is, to get more practice drawing Lewis structures. I know if you have me for class, your midterm isn't due until Sunday. So this will further get you more comfortable with Lewis structures prior to taking your midterm. And so in addition to drawing Lewis structures today, once we've drawn the Lewis structure, then we're going to focus in on that central atom of our Lewis structures. And we're going to apply a theory called the VSEPR theory, which stands for Valence Shell Electron Pair Repulsion theory. It's also been called Valence Shell Electron Group Repulsion theory by more modern textbooks, but I still use the pair instead of the group terminology. So we know that a theory in science is something that explains best why something occurs. And so a theory becomes accepted by reputable people in the profession. But the theory is never actually 100% proven to be correct, but it is accepted to be correct by So we're going to look at the results of the VSEPR theory, which tells us a good explanation as for why the molecules that we're going to look at today have the Lewis structures that they do, which gives them a particular, what's called molecular shape or molecular geometry. So one premise of the VSEPR theory is that when atoms get together and share electrons and form covalent bonds, these atoms that make up the molecules don't want to be crowded when they come together and share electrons. They want to be as far away from each other as they can possibly be, while at the same time sharing electrons with each other. And so because we're not in the lab, if we were in the lab, you would be doing this. But because we're not in the lab, you're going to just view models of the Lewis structures that you will draw. And based on the models, you're going to hand draw your own representation of a model of this particular molecule that you've drawn a Lewis structure for. And then you're going to use this little data table at the end of our document, and you're going to predict the bond angle for each of your Lewis structures and the molecular geometry, which is also called the molecular shape. And so it's the VSEPR theory that these atoms want to be far apart from each other as they can possibly be, and therefore is going to give the Lewis structure of the molecule particular bond angles that represent how far apart these atoms are from each other. And that particular bond angle is also going to give rise to a particular geometric shape for the molecule. And so we started out already with methane. We already drew its Lewis structure, having a total of 8 valence electrons. And so in our Lewis structure, we decided that carbon was the central atom. And so now we're going to focus in on this central carbon atom. We connected that central carbon atom to the 4 outside hydrogen atoms with a single bond between that central carbon and each of the 4 outside hydrogen atoms. Notice there are not any lone pairs of electrons around the central carbon atom. But we have 1, 2, 3, 4 single bonds around that central carbon, and 0 double bonds and 0 triple bonds. And so if we take a look at question 4, which asks us how many total groups are around the central atom, meaning how many total electron groups are around the central atom, what would your answer be? How many groups of electrons are around the central carbon atom? Anyone? Thank you, Whitney. 4. That is correct. So, Whitney, of these 4 electron groups that are around the central atom, are any of these groups lone pairs?
No.
Very good. Thank you. And so these 4 single bonds that are connecting the central hydrogen to the central carbon to the outside hydrogens, these are all bonding electron groups. So there are various electron group types. You can have bonding electron groups, or you can have a non-bonding electron group. So each of these different types count as only one type of group. A single bond is an electron group. It's only one electron group. A triple bond is one electron group. A double bond is one electron group. A lone pair of electrons is one electron group. So when you're counting up how many electron groups are around a central atom, you count each of these entities as one electron group. Any questions about that? Laura, are you good with that? You have a question?
Can you hear me?
Yes.
Oh, I said no. I may have said it too soon.
Okay. So we have 4 total electron groups around the central carbon in methane, and all 4 of those electron groups happen to be single bonds. So they are all bonding electron groups, and they're all single bonds. None of those are lone pairs. None of them are a non-bonding group. So now if we go to our eLearn Lab homepage, click on the course content tab. If you're not there already, go to week 7, and hopefully you've already downloaded and you've been filling it out as we've been going along here. But I want you to also download the pictures for the molecular models, because you're going to need those pictures as you complete the rest of the lab. So let's take a look at the picture for the model for methane. So there's a PDF document called, or Word document, I can't remember which, for Lewis Structures lab models. Make sure you download that document. So here is the methane. And we have both a ball and stick model here, as well as what I call a marshmallow and toothpick model here. And they are telling you the same information. Looking at the ball and stick model, the black sphere is our carbon atom. The 4 white spheres represent our 4 hydrogen atoms. And then you have the 4 sticks. Those are representing your 4 single bonds. Now the marshmallow and toothpick model are telling you the same information as the ball and stick model. You've got your central carbon atom shown as the pink marshmallow. And then the 4 white marshmallows represent the 4 hydrogen atoms. And then the 4 toothpicks, of course, representing your 4 single covalent bonds. And so based on those model pictures for methane, we go on to part 2B. And so because we're not in lab in person, if we would have been, you would have made these models yourself. But in lieu of that, you're viewing the pictures. So based on the pictures that you see, draw your own model for methane. So I'll put a sphere in the center for my carbon atom. Then I put my 4 stick. And I'll choose another color for my 4 hydrogen atoms. So there's my methane model drawn. If you don't have colored pencils or colored pens, you can just do it all in black ink or blue ink or whatever you have handy. So there's our shape. That's question 6. Now we move to question 7 and answer the question about the bond angle. What angle is between basically the sticks or the toothpicks? And so what we're talking about is this angle between the sticks. Yes, this lab report form is available in eLearn. I'm not sure why you're not seeing it. Cameron, let me stop sharing here briefly. So go to eLearn, our lab eLearn page, click on week 7. And there it is right there, Lewis Structure Lab Report Document. Are you good with that now, Cameron? I don't have any restrictions on this document. I had lab yesterday. There were actually 3 lab sections yesterday, and no one said that they couldn't download the document. I had a lab section yesterday myself. There were no problems. And there are 2 other instructors who had labs yesterday. No one had a problem downloading it. So if you go to our eLearn homepage, click course content, click on week 7 in the table of contents. And I tried to separate things so that things were clear. There's the lab report document, and it's giving you some instructions about what you need to turn in this week. And you just click on it. And I don't have any restrictions for downloading. There may be a technical issue on your end, but you should be able to download it just fine. It's just a PDF file. I would advise you, if you can't download it right now, have a copy of it up on your document and write everything down as far as the answers to the questions by hand on regular notebook paper, and then transfer the information to the data sheet once you can get it downloaded. But there's no problem with the documents, not that I'm seeing, and I haven't heard about any problem until now. And like I said, there were 3 lab sections that met yesterday. Okay. Okay, so going back to where we left off, and Whitney gave us our answer for our bond angle for our methane molecule. If we go back to the end of our document, to the data table I referred to earlier, we said that methane has 4 electron groups around it, and 0 of those 4 groups were lone pairs. So that means that the shape of methane is tetrahedron, and its bond angle is 109.5. Whitney, I think you said 109, which is not quite correct. In order for the bond angle to be 109, 1 of those 4 electron groups has to be a lone pair. And that's not the case for methane. So methane's bond angle is 109.5 degrees. And the shape, tetrahedron. Or you could say tetrahedral, which most older textbooks refer to it as tetrahedral. And so these are the same types of questions that you're going to answer for each molecular compound that we're drawing the Lewis structure for today. So I've done the first one, the first model with you, which was just going over the instructions for drawing Lewis structures. We've gone over the second model together, which I included in the instructions, methane. So I'm going to go through one more with you, and then I'm going to send you to your individual group meeting rooms to finish the rest of the Lewis structures with your group. So the next molecular compound is ammonia, formula NH3. So which atom, nitrogen or hydrogen, will be the central atom? Very good, nitrogen, because remember, hydrogen can never be the central atom. So we're going to put nitrogen in the center, and we're going to use single bonds to connect the 3 hydrogens to the central nitrogen. And then following step 2, we're going to do our valence electron count. There's 1 nitrogen in the formula, and nitrogen is in group 5. There are 3 hydrogens in the formula. Each are in group 1. So ammonia has a total valence electron count of 8. So is my Lewis structure complete and correct?
No.
The way it is? No. So I have to move on to step 3, don't I? How many electrons have I already put into my Lewis structure?
6.
Very good. How many do I need?
2 more.
Right. So where do I put those 2 more? Who's not happy?
Nitrogen.
Right. So where do I put those 2 remaining electrons?
On the 4th empty, yeah, on top.
Very good. Now, is my Lewis structure correct?
Yes.
Do I need to worry about double bonds and triple bonds? Do I need to move to step 4 of our rules?
No, because there's an octet.
Very good. We have an octet, or 8 electrons around our central nitrogen. Hydrogen is an exception, is happy with just having 2 electrons around it. So our Lewis structure is done. We don't need to worry about double and triple bonds in ammonia. We don't need to move to step 4 of our Lewis structure drawing rules. So now we're ready to answer the remaining questions for Model 3A and Model 3B. So we said our nitrogens is our central atom. For question 10, question 11, count up the following groups around the central atom and indicate how many of each type of group of electrons there are. So how many lone pairs of electrons are on the central atom?
One.
Very good. How many single bonds are around the central nitrogen atom? Very good. Thank you, Hannah. And we said there are no double bonds and no triple bonds. So how many total groups are around our central nitrogen atom? Thank you, Whitney, for how many of these groups are lone pairs?
1.
Very good. So now we'll go to, thank you, Kennedy. We'll go to our model pictures for this week. We've already looked at methane, so now we're going to move on to ammonia. And so again, we have both a ball and stick model and a marshmallow and toothpick model. And so in the ball and stick model, again, our white spheres represent the hydrogen atoms. There are 3 of them. And the black sphere represents the nitrogen atom. And notice here is a stick. But there's no atom attached to that stick. So that stick with no sphere or atom connected, that represents our lone pair of electrons that sits on the nitrogen atom. And going to the marshmallow model, again, the white marshmallows represent the 3 hydrogens. The pink marshmallow is our nitrogen atom. And then we've just got a toothpick with no marshmallow attached to it. That too represents the lone pair of electrons sitting on top of that nitrogen atom. So based on our 2 models for ammonia, draw your own model of the ammonia molecule on your data sheet. So my red spheres are my hydrogens. And then that stick with no atom attached, that of course is my lone pair of electrons. So now again, we go to our data table at the end of this document. And so now we have the situation where we still have 4 groups total, but now one of those groups is a lone pair. So our shape is not tetrahedron this time for ammonia. So ammonia and methane have different shapes. Ammonia's shape is trigonal pyramid. And its bond angle is not 109.5, but it's a little bit smaller than that. It's about 109. This little squiggly line means about or approximately. So our bond angle is 109. And our shape is trigonal pyramid. And so we notice in our table that there are 2 different types of geometries listed. Electron geometry, which we'll deal with this during our week 9 lab. We'll cover that extensively in chapter 4, the difference between electron geometry and molecular geometry. So we'll dig a little bit deeper into that for when we return from fall break. But today we're just interested in the molecular geometry or the molecular shape and bond angle. So notice that methane and ammonia both have the same electron geometry, tetrahedron, but their shape or their molecular geometry, which describes the spatial arrangement 3-dimensionally, it's different because methane has 4 bonding groups, whereas ammonia only has 3 bonding groups and 1 non-bonding group represented by that lone pair of electrons. And that's going to affect both the 3-dimensional shape and the bond angle. So now that we've answered all the questions for models 3A and 3B for ammonia, the next molecule is water for model 4. And then you'll have model 4B, in which you'll use your model picture for water, and you'll sketch your own model and use the table at the end of the document to answer the bond angle and shape questions. You'll do the same for model 5 involving ozone and model 6 for carbon dioxide, CO2. So go into your group meeting rooms, answer questions number 17 all the way through 41 for models 4A, 4B, 5A, 5B, 6A, and 6B. You and your group members are done answering those questions. Return to the general room where you can ask any questions that you may have about models 4, 5, and 6. During this time period, I'll be coming into each of your individual group rooms to see if you need any assistance. And then, of course, you'll be returning to the general room. I estimate that it'll probably take you about 30 minutes or so to finish up these last 3 models. And so let's meet back in the general room at about 10:35, and then we'll answer any of your questions that you may have. Now, I've mentioned that we're going to be using this data table of information in week 9, to focus on things like electron geometry, but also other things like revisiting molecular geometry and shape, as well as a term that we'll also focus on in chapter 4, polarity. So in addition to finishing up this data sheet for models 4, 5, and 6, after we meet back in the general room and I answer any questions that you may have, and I'm going to stop presenting this screen briefly here. So once you've got models 4, 5, and 6 complete and you're confident in that, you're going to have one last task to do today. So if you go back to our eLearn page for this week, if you haven't downloaded the model pictures yet, there's the Word document for the model pictures. And then we're going to revisit Lewis structure concepts again 2 weeks from today during week 9. So today I also want you to download the Lewis structures for week 9 document. And basically there are 17 molecular compounds shown here that you need to draw the Lewis structures for, and have these Lewis structures when you come to class during week 9. Now, some of these Lewis structures we're drawing today, like water, ammonia we just drew, methane, we just drew that one, and you're going to draw CO2. And if you're in my lecture class, we've also drawn some of these in lecture. Some that I know we've drawn in lecture: oxygen, O2, nitrogen. We've also drawn SO2, N2O, SO3, so on and so forth. But some of these we haven't drawn in my class. Some of these may be totally new to you. So you want to have these Lewis structures drawn for week 9. And so our week 9 lab will be held on October 23rd. And so by 8:50 a.m. on 10/23, you need to have this document completed with the Lewis structures drawn. And there will be a Dropbox set up for week 9 Lewis structures. And you'll submit this document with completely drawn Lewis structures to that Dropbox before your week 9 lab meeting. So the Dropbox will close at 8:50 a.m. And so each of your lab reports counts 100 points. So for week 9, these Lewis structures that you are to draw prior to lab will count for 10 points of your 100. And I'm not going to grade these Lewis structures based on correctness, just completeness. As long as you've drawn a Lewis structure for each of these 17 compounds, you'll get the 10 points, okay? And then during week 9, I'll release a key for these Lewis structures so that if you miss 1 or 2 of them, it's no problem. You'll be able to complete week 9 by looking at the actual key for these Lewis structures, just in case there were any of them that you didn't get correct on your own. And so these Lewis structures, we're going to be determining the electron geometry, molecular geometry, and polarity for during week 9, okay? So all you need to start working on today, after you complete the data sheet for week 7, you can start working on these Lewis structures for week 9. And my class yesterday, I gave them the option to stay around in class the entire time and work on these Lewis structures. Or if you choose to leave the meeting once we meet back in the general room and you ask any questions you have about this week's lab, if you want to go ahead and leave the meeting and work on these Lewis structures, because you've got about 2 weeks to get them finished anyway, if you want to go ahead and leave the meeting and work on these Lewis structures on your own time, you have that option as well. Now, are there any questions? What you're turning in by tonight at 11:59 p.m. is just simply this week's lab report. So today, by 11:59 p.m. tonight, this is the document that you're turning in, this completed document. The week 9 Lewis structures, this was for my other class yesterday. For you, it's going to be due by 8:50 a.m. on 10/23. So this is going to be your pre-lab assignment for week 9. Everyone understand what's due by tonight at 11:59 p.m. and what's due by 8:50 a.m. on October 23rd. And again, I will create a Dropbox for this pre-lab assignment. If there aren't any questions about what's due for you today, go ahead and go into your group rooms and complete models 6, 5, and 4 for carbon dioxide, ozone, and water. Come back into the general room in about 30 minutes from now, and I'll answer any questions that you have. And I will be jumping in to your individual group rooms to check in on you over these next 30 minutes. Again, make sure you're going into your group meeting room at this time and work on the last 3 models with your group members. Again, if you don't remember what group number you're in, go to the chat box. I have pasted the group numbers and members in the chat box. For those that are in the general room, one question that I've seen concerning ozone in Model 5, question 33, the geometry or shape, or what we call molecular geometry for ozone, is bent, B-E-N-T. And you should have also seen that the molecular geometry or shape for water is also bent. But what you also should have known is that for ozone, the bond angle is much larger than for water. Ozone's bond angle is 120 degrees, whereas the bond angle for water is only 109 degrees. I want you to, I don't want you to just ask me the question and I give you the answer. I want you to look at all the data and compare the ozone data to water. How many total electron groups does water have versus how many total electron groups that ozone has? If there's a difference in the total number of electron groups, that could account for the difference in the bond angles. So take a look at what's alike between ozone and water to answer question 33, but then focus on what's different about the Lewis structures of those two. Do they have the same total number of electron groups around their central atoms? If not, that's going to cause them to have different bond angles. So that's how you should approach question 33. So some of these questions, like number 33, just requires a little thought after you actually look at your data, analyze your data, compare the data for ozone and water, and in comparing the data, you should say, oh, this is what's different about those two. That must be accounting for the difference in the bond angle. So you need to start thinking logically and analytically like that, and use your critical thinking skills to answer questions like number 33. Yes, Destiny.
Okay, so for Model 6, on the when we had to draw the shape, I already talked to my group about it, but in the Word document, sorry, in the Word document, it only shows like one toothpick holding to the carbon and oxygen models.
I'm showing models now. Yes. There's your central carbon.
Okay.
Those are your two oxygens.
So I was just
it's just one stick. That's still the double bond.
Okay.
These were done last semester when the shutdown happened. I say, why do over again what's already done? And in most models, you can see there's just one stick, and that's still representing a double bond.
Okay. I just wanted to be sure. All right, thank you.
And so I did the ozone one myself, like yesterday.
Mm-hmm.
And so I got a little fancy with mine. I put two toothpicks there. I actually showed the double bond, but I didn't have to. I just chose to do that.
Oh, okay.
Extra step. But no, you don't have to do the two sticks.
All right, I just wanted to be sure. Thank you.
It is okay if you do.
Okay.
So yes, there is a double bond between the carbon and the oxygens in CO2. And so for your model, this is fine. You have your carbon atom represented. your 2 oxygen atoms, and then a single stick. Or you can draw a really thick stick if you want to represent the double bond. And I think most of us are back in the general room. Any other questions about models 4, 5, or 6? So for question 33, water versus ozone. Water's Lewis structure looks like this. Ozone's Lewis structure looks like this. Ozone has an oxygen central atom. The other 2 oxygens are your outside atoms. There are only 3 electron groups around the central oxygen of ozone. But for water, you have 4 electron groups around the central oxygen. You got 2 bonding groups and 2 non-bonding groups, giving you a total of 4. So therefore, ozone's bond angle is about 120 degrees, whereas oxygen's bond angle is much smaller, about 109. So you got the angles, the bond angles for ozone and water are very different, even though both of their shapes are the same. So they both have bent shapes or bent geometry, but their bond angles are different. And these bond angles are different because of the different number of total electron groups around their respective central oxygens. And that's what gives the difference in the bond angles. Any other questions about number 33 for Model 5B? Any other questions for models 4 through 6? Okay. If there aren't any other questions, then make sure that you've uploaded this document with all questions numbers all the way through number 41 completed, and upload this completed document to the week 7 Lewis Structures Lab Dropbox by 11:59 p.m. tonight. Your Lewis Structures document for week 9, you will not submit this document to the week 7 Dropbox. I will create a special Dropbox for this document that is not due until 8:50 a.m. on October 23rd. And I'll have the Dropbox set up sometime this weekend. So once you finish drawing all your Lewis structures for week 9, go ahead and upload the document at any time before 8:50 a.m. on the 23rd. And I'll try to get that Dropbox set up sometime over fall break. And so you can either stay in the meeting once you're done with today's lab data sheet, and you can start working on your Lewis structures, or if you would like to leave the class meeting early today, you're free to do that as well. Have a good fall break. If you are in my lecture section, remember that your Chapter 3 homework and quizzes are due by tonight as well, and your midterm exam is due by Sunday night. Again, any questions about models 4, 5, or 6? And again, make sure that you complete this document today and upload it to the week 7 lab Dropbox by 11:59 p.m. tonight. Your week 9 Lewis Structures document is not due until October 23rd, 8:50 a.m. But I will have the Dropbox set up early so you can submit it but way before the 23rd if you like. Any questions? Models 4, 5, or 6? If not, I'm going to go ahead and stop the recording